All right, let's talk about section 2.5, the chain rule. Okay, this talks about how do we take derivatives of compositions of functions. As you guys will see on the videos that I've posted on the section before, that you can take derivatives of products of functions using the product rule. So d dx of some f of x times g of x. This is called the product rule. This says this becomes the derivative of f times g plus the derivative of g times f. This is the product rule right here. Okay. Then remember, we've learned the quotient rule. This says that the derivative d dx of a ratio or a quotient is the bottom function times the derivative of the top minus the derivative of the top times the bottom. I just repeated myself. Minus derivative of the bottom times the value of the function of the top. Everything divided by the function in the denominator squared. So this is the quotient rule. Here's the product rule when you have two functions multiplied times each other. Here's the quotient rule when you have two functions divided by each other. Recall, if you have two functions added or subtracted to each other, this one's easy. F of x plus g of x. The derivative travels to each of them. This becomes d dx of f of x plus d dx of g of x. So this just becomes f prime of x plus g prime of x. And we could have put a minus here as well. It works for plus or minus. So this is the sum and addition, division and multiplication. That's it, right? There's no more to do, right? Functions are that simple. Functions are just like numbers, and all you can do is multiply, add, subtract, and divide, right? No, actually functions are actually you can do more with functions than numbers, because with functions, you can plug them into other functions. This is a process known as function composition. So the chain rule tells us how to take this derivative. How do we take this derivative? d dx of f of g of x. Recall, this is function composition. It's g composed with f of x. Okay, so let's derive this. And first, to do so, we need to talk about the local linearity formula, which is very important. Local linearity gives us that f of k plus alpha approximates to f of k plus alpha f prime of k. Okay. So let's apply that to f of g of k plus alpha, because this is the same thing as d dx of our f of g of x. Actually, we can change this to an x instead of a k, and now it's more accurate. Okay, so this becomes f of g of x plus alpha minus f of g of x all over alpha by definition of derivative. So by local linearity, we can break this down to f of g of x plus alpha g prime of x minus f of g of x all over alpha. And here comes the tricky part. Remember in local linearity, f of k plus alpha, this is a real number. This is an infinitesimal. So a real plus an infinitesimal gives us a real plus an infinitesimal times the derivative. So the same is going to happen over here, okay? Because g of x is now the real number, and alpha g prime of x is now becoming the infinitesimal. So we can use the local linearity twice. So what does this give us? This gives us f of g of x, okay, plus alpha f prime of alpha g prime of x. Minus f of g of x. Let's see if I did this right. Yes. This becomes f of g of x plus alpha g prime. Oh, yeah. This got a little messed up here. F of g of x, this needs to say, and put this alpha right here. This middle term did get messed up. Here's our infinitesimal, alpha g prime of x, being multiplied times our derivative, f prime of g of x. There we go. This was our infinitesimal. This whole thing was our infinitesimal. So this whole thing replaces the role of alpha in the normal local linearity formula. And now f prime of g of x is replacing f prime of k. Recall everything is divided by alpha. So then this cancels and this cancels. So all that we're left with here is alpha g prime of x, f prime of g of x, divided by alpha. So the alphas cancel. So we get g prime of x, f prime of g of x. And this is equal to d dx of f of g of x. This right here. So this means d dx of f of g of x is is equal to f prime of g of x times g prime of x. So this is the chain rule. This is how derivatives operate on function composition. Okay? It'll make more sense when we apply it. Right now it seems like, what are we doing? How does this get applied? You guys don't need to know how to derive this. You guys need to know how to apply this. Although you may be rewarded if you do know how to derive it. I may put that as extra credit on the test. Hint, hint. So another way to write this chain rule is that the d dx of some f of u is going to be equal to df dx. Or actually, let's write it as f prime of u du dx. This is another way of saying the chain rule. This is Leibniz notation chain rule. So what does this mean? Let's actually put this into practice. Because right now it's just a bunch of, why are we doing this kind of stuff? So let's take the derivative d dx of sine of 3x minus 5. All right. Before we start using the chain rule, let's notice this function right here. I'll bring it over here and I'll rewrite it. Sine of 3x minus 5. Notice that this is really two functions. The first function, let's call it f of x, is equal to sine of x. The second function, let's call it g of x, is equal to 3x minus 5. So f of g of x is equal to f of, and we can replace f as sine of, let's keep it as f of 3x minus 5, right? But recall f of x is equal to sine of x, so this becomes sine of 3x minus 5. So notice we've built sine of 3x minus 5, our function right here. We built it as a composition of two functions. We plugged in 3x minus 5 into sine of x to obtain sine of 3x minus 5. So when we take the derivative of said function, you have to apply the chain rule, because the chain rule applies to a composition of functions. So first, the chain rule says, okay, take the derivative of the outside function and leave the inside function constant. Then take the derivative of the outside function. So the derivative of the outside function, sine, if you watch the videos of the previous sections on trigonometric derivatives, the derivative of sine is cosine. And then we keep the inside function constant. So the outside function becomes sine, the inside function becomes constant, but we're not done. We have to do this part. So that's d dx of the inside function, multiplied times the whole value. And when you take the derivative of this function, the derivative of a constant is 0. And the derivative of 3x just takes the x away and you're just left with a 3. So this becomes 3 cosine of 3x minus 5. It's this right here. We're using the chain rule. Let's do another problem. What about d dx secant of x squared plus 3x? So we take the derivative of the outside function. If you watch the section on trigonometric derivatives, that's 2.4. The derivative of secant is tangent, the derivative of secant x. Remember, d dx of secant x is secant x, tangent x. So the derivative of secant of x squared plus 3x is then going to be secant of x squared plus 3x, tangent of x squared plus 3x. Don't forget now d dx of the inside function. So then this just becomes a secant of x squared plus 3x, tangent of x squared plus 3x. The derivative of this, we bring down the 2 with the power rule. This becomes a 2x. The x goes away here, so this becomes a 3. And we're done. Now that we have memorized the chain rule, let's clear up more space so we can do more problems at once. What about okay? The derivative of cosine is negative sine. Remember, d dx of cosine of x, negative sine of x. So d dx of cosine of 4x squared is negative sine of 4x squared times dx of the inside function. So then this equals negative sine of 4x squared times this 2 comes down, gives me an 8x. The 2 comes down, minus 1. Remember the power rule, guys? d dx of some x to the n is n x to the n minus 1. So for example, dx of x to the 80 is 80 x to the 79. dx of 2x to the 4th, for example, is 2 times 4 times x to the 3rd. We'll just decrease that power by 1. So, interestingly enough, d dx of square root of x is the same thing as d dx of x to the 1/2 power. So when we bring that 1/2 down, x to the 1/2 minus 1 gives us 1/2 x to the negative 1/2. But that, remember from algebra, that's equal to 1 over 2 x to the 1/2 power. And then x to the 1/2 is just a square root. So this becomes 1 over 2 square root of x. And that's what the derivative of the square root of x is. It's 1 over 2 square root of x. Back to this, here we're done. I just wanted to show you examples of how to apply the derivatives over there. Let's do another example. What about d dx of 5 cosine of x cubed minus x? Remember that the derivative ignores constants. So this just becomes this. It ignores that 5. Next, the derivative activates, and the derivative of cosine, remember, the derivative of cosine is negative sine. If you don't know why this is true, let me actually write it out. The derivative cosine of x, negative sine of x. If you guys don't know why this is true, check out the video on 2.4. I derived that, and section 2.4, they derived that. Okay, now we're over here, so the derivative of cosine is negative sine, so this becomes 5 times negative sine of x cubed minus x. d dx of the inside function. So this becomes 5, or negative 5, sine of x cubed minus x times the power rule. So remember, d dx of x cubed minus x is the same thing as d dx of x cubed minus d dx of x. So this becomes 3x squared minus a 1. Why does this become a 1? Why is the d dx of x equal to 1? Well, notice that d dx of x is the same thing as d dx of x raised to the first power. So this becomes a 1 times x raised to the power minus 1. So we get 1 times x raised to the 0. And anything raised to the 0th power is a 1. So you get 1 times 1, which is a 1. That's why that's happening, if you were wondering. And so this becomes 3x squared minus a 1. And you're done. Okay. What if we have g prime of t equal to tangent of 4t? Or I mean g of t is equal to tangent of 4t. What is g prime of t equal to? Well, g prime of t is d dt of g of t. That's d dt, the derivative of tangent of 4t. When I write d dt, guys, that's just like mathematical notation for perform the operation of the derivative. And when you study chapter 2.4, you realize that the derivative of tangent is secant squared. So this becomes secant squared of 4t, but you got to take the derivative of the inside function, that 4t. So this becomes secant squared of 4t times d dt of 4t is just a 4. So our answer is 4 secant squared of 4t. What is the derivative of sine of cosine of x? Well, the derivative of the outside function, derivative of sine is cosine, and we keep the inside constant, times d dx of the inside function. So this becomes cosine of x. The derivative of cosine is negative sine. And you're done. What about d dx of sine of x times cosine of x? Notice that this is no longer the chain rule, it's the product rule. So we might as well practice it. This is a product of two functions, where f of x is sine of x, g of x is cosine of x. Recall that the product rule states that the product of two functions, its derivative is f prime of x, g of x, plus g prime of x, f of x. That means this equals the derivative of sine, which is cosine, times cosine of x, plus the derivative of cosine, which is negative sine, times sine of x. So this gives us cosine squared of x minus sine. So now let's talk about the power rule, chain rule. Well, it states that if you take the derivative of some x to the n, or actually in this case, let's say u to the n, where u is a composition of two functions, then you get n u to the n minus 1 times du dx. Where remember u is equal to some like composition of two functions. What's an example of this? This is y of x. I mean, what is y prime of x? Well, y prime of x, by definition, is dx of y of x. And that's dx of x squared plus 1 raised to the 5th power. So we do the power rule first. We'll bring that 5 down times x squared plus 1. 5 minus 1 is a 4. Now ddx of the inside function. So then this equals 5 times x squared plus 1 to the 4. ddx of the inside function gives us a 2x. So when you simplify, this becomes 10x times x squared plus 1 raised to the 4th power. Here's another example. What if our y of x is 4x plus 7 cubed, quantity cubed? Then y prime is just ddx of this. So this becomes 4 times 3x plus 7 raised to the 2 ddx of the inside function. The derivative of 7 is 0, and the derivative of x is 1, so this whole thing is just 1. 1 times anything is itself. So this reduces to itself. 4 times 3 is 12. So you get that. So you guys are getting the hang of this. So let's do something. Let's kick it up a notch. What is the derivative of this guy? That looks scary, huh? It's a big square root. Nah, it's not that bad. Notice that we break this down to this. Okay, but then we just use the power rule. That 1/2 comes out in front. I put a negative 1/2 here. Why is that negative 1/2? Because 1/2 minus 1 is negative 1/2. 1/2 minus 1 is 1 minus 2 all over 2, 1 over 2. So that's why that becomes a negative 1/2. But we're not done, because you have to take the derivative of the inside function, ddx of the inside function. Bring this up over here. So then we get 1/2 4x plus 7 raised to the negative 1/2 times the derivative of the inside function. We use the power rule for each of these. So this becomes a 3x squared. This just becomes a plus a 4. And that goes to 0. You could leave it like this if you want. But another way of representing it is this. So potato, potato, tomato, tomato, it doesn't matter. Either one of these actually works. This is equivalent to that. So, and let's do another example. What's the derivative of this guy? Well, that's just take that square root away and just raise the whole thing to the 1/2 power. Then bring the power down. Rewrite what you had before. -1, so it becomes a -1/2. -1. Take away 1 from 1/2, you get -1/2. Then ddx of the inside function. So you end up getting, this is 1/2 times x squared plus 6x raised to the -1/2 power times ddx of the inside function. We use the power rule here, so that brings the 2 down, so you get a 2x. And then when ddx operates on 6x, it removes the x and it just becomes a 6. So here you go. You could just say you're done here. But recall, this whole thing raised to the -1/2 power is as if this whole thing is square rooted inside the denominator, down below the denominator. So this becomes a 2x plus 6. That 1/2, the 2 appears down here. And we got, there you go. What about ddx 5x squared times 11x minus 8 raised to the 4th power? Okay. Notice we're going to have to use the product rule and the chain rule. Okay. The product rule is going to work on this function, call this f of x, and this function, call it g of x. So g of x is, for example, 11x minus 8 raised to the 4th power. But g of x is a composition of 2 functions. If h of x is 11x minus 8, and let's say psi of x is equal to x to the 4th, then psi of h of x is equal to g of x. Why? Psi of h is the same thing as 11x minus 8. But then when you plug that into psi, you get so notice we're going to have to do the product rule first and then the chain rule, because g of x is really a composition of 2 functions, a psi of h of x. So this is going to be a fun example. So first we do the product rule. So we're going to say 5x squared prime times 11x minus 8 raised to the 4th plus 11x minus 8 raised to the 4th prime times 5x squared. I put that prime is there as if it's like a ddx. So ddx of f of x can be shorthand f prime of x. So we don't have to keep writing ddx. We could just write f prime of x. All right. The derivative of this becomes 10x times this guy. This comes along for the ride. Now we got to take the derivative of this. But there's going to be a chain rule afterwards. So bring out the 4, 11x minus 8, raised to the 3rd power, then ddx of the inside function, 11x minus 8. And don't forget to carry down that 5x squared. So this becomes 10x times 11x minus 8 raised to the 4th power. And then this, the differential operator, when it hits that 8, it goes to 0. And when it hits this 11x, it just becomes an 11. So this whole thing just becomes an 11. And 11 times, so now we have 11 times a 4 times a 5. What do we get there? That's 11 times 5 is 55 times 4. So that's 120. 55 times 4? Yeah. So 4 times 50 is 200, and 4 times 5 is 20, so 220. So this becomes 220 x squared times 11x minus 8 cubed. See what I was doing there, guys? I had to multiply this 4 times this 5 times this now 11. So that's why I was thinking so long, because I'm very slow at arithmetic mentally slow at arithmetic. I never was fond of doing arithmetic in my head, but I should try. I should practice and get better. Let's do a few more examples before doing a conceptual explanation of this. What's the ddx, or the derivative of sine squared of 5x squared? Okay. Recall, this is the same thing as ddx, sine of 5x squared times itself. So now we're going to do a product rule, and then it's going to invoke a chain rule, because this is a function, this is a function. We do the product rule first, and then it's going to invoke the chain rule. So the product rule says that we got sine, we need more space. Sine of 5x squared prime, sine of 5x squared, plus sine of 5x squared prime times sine of 5x squared. Okay. Notice that we can now write this as 2 times sine of 5x squared prime sine of 5x squared. So that makes it simpler, because it's the same thing. Now we have to take the derivative of sine of 5x squared. So notice this becomes 2 sine of 5x squared times dx of sine of 5x squared. This is going to involve the chain rule, because first we take the derivative of sine, keep the inside constant, then ddx of the inside function. So this is going to become 2 sine of 5x squared times the derivative of sine, which is cosine, 5x squared x of 5x squared. So then bringing the calculation up here, we get 2 sine of 5x squared cosine of 5x squared times, what's the derivative of this? The 2 comes down, multiplies times 5 to give me a 10. And then that 2 minus 1 is just a 1, so it just becomes x to the 1, which we'll just leave as x. We can simplify this further, let that 10 and that 2 meet up, so this becomes 20x sine of 5x squared cosine of 5x squared. Do another kind of example like this. Something similar. What's the ddx of the cosine squared of 4x cubed? Okay, remember, again, this is ddx of the cosine of 4x cubed times itself. So then we use the product rule. So this becomes cosine of 4x cubed prime cosine of 4x cubed plus cosine of 4x cubed prime cosine of 4x cubed. But this ends up becoming just something added to itself. So this becomes 2 cosine of 4x cubed prime cosine of 4x cubed. Now, let's focus on what this cosine of 4x cubed prime means. So let's combine that. 2 cosine of 4x cubed times the dx of cosine of 4x cubed. That's what the cosine of 4x cubed prime really is. So then that equals 2 cosine of 4x cubed. Derivative of cosine is negative sine times negative sine of 4x cubed. Don't forget d dx of the inside function. So the d dx of the inside function is, so let's rewrite everything. So this becomes a minus 2 cosine of 4x cubed sine of 4x cubed. What's the derivative of 4x cubed? Well, the 3 comes down to give us 12. And then we subtract that power by 1. So 3 minus 1 is 2. Boom, you're done. You could simplify this further by combining the 12 and that negative 2 to give us negative 24 x squared cosine of 4 x cubed sine of 4 x cubed. This would be our simplified final answer. Okay, so I hope that all these worked examples will allow you guys to do these problems with confidence. I recorded this lecture with nobody here, so class is now normally in session. So please come to class on, what's today, Wednesday, Friday. Please come to class on Friday, everybody who's watching this. And I'll send out an email notifying you guys of doing that as well. I won't count you guys absent because I put you out of routine, but definitely you guys need to come back to class, and so do I. So happy to be back. Hopefully I'll see you guys soon.